Hello.
Hello, and welcome to The Sky at Night, although this programme is about the sky by day.
That's because we're talking about the sun. It's just an ordinary star, one of billions in our Milky Way galaxy, but it's important to us here on Earth because it provides our heat and our light.
We've come to the Royal Observatory Greenwich to tell the story of our sun, the monarch of the solar system.
And Chris North will have news from the very edge of the solar system, where it turns out things are a little bubbly.
And Pete and Paul will be giving advice to some newcomers to solar observing.
Astronomers have been studying the sun at the Royal Observatory Greenwich for more than 350 years. It was their job to measure the midday sun with their transit telescopes, setting the watches of the city, the country, and the world. The meridian ball still drops at precisely 1 p.m. The first Astronomer Royal, John Flamsteed, is still remembered today in the name of the Flamsteed Society, the Royal Observatory's resident amateur astronomy group. Today, they're setting up in the courtyard for some solar observing. Protecting your eyes when looking at the sun is critical, and these telescopes have astronomical filters to make them safe. Pete and Paul are finding out how we can look at the sun safely, although today it's proving rather elusive.
So Rupert, talk me through what you've got set up here.
Okay, well this is just a conventional nighttime telescope,
Right.
Refractor, but to allow us to view the sun, we just have this homemade filter.
Right, okay.
Which uses a special material,
Yeah.
which is safe to look at the sun. So using that will give us a white light image. So you see all the sunspot detail,
Right.
and any surface granulation. So it's quite an enjoyable and simple way to observe the sun.
What sort of telescope is this?
This is a hydrogen alpha telescope.
So this is, unlike when we're looking in white light, this gets all those lovely red images. It sees further into the sun, doesn't it?
It does.
What do you enjoy most about solar observing?
I think it's something you can do in London without any light pollution, and we can do this here the same as we can do anywhere else in the country.
Yeah.
We can do it in the daytime and keep warm, unlike and not
Hoping to
today.
look like, hoping to see it myself, but it doesn't look likely at the moment. Well, Pete, we were hoping to do some solar observing today, and look at it, it's nothing but cloud and snow.
But we have got some footage we took earlier, and that really shows the dynamic nature of the sun.
We have indeed. There's some lovely objects on there. There's some prominences and all sorts of interesting things.
But we should talk about how to actually get into solar observing, because it doesn't need to be an expensive thing to actually take up.
No, it doesn't. Let's look at the sort of very basic end of it, the white light area of solar astronomy, and should perhaps explain what we say is white light isn't really a colour. White light is in fact composed of all the colours of the rainbow.
Yeah.
But you can see quite a lot of the sun in white light. You see some interesting objects, can't you?
You can. It is a very cheap way of getting into solar
It doesn't
observing.
come cheaper than that.
Well, you get a piece of white light filter like this from an astronomical stockist for about £20 for an A4 sheet.
That's reasonable.
And then you have to make it yourself. But once you've made it, you can then slip it on the end of a nighttime telescope. It converts it into a telescope which is safe for solar viewing.
It looks rather flimsy, Pete.
Well, it does, but it is actually quite tough stuff. But this rejects 99.9% of the incoming light from the sun, so
Right.
it reduces the sun's levels to a safer value.
And when doing that, then you can see some of the things that you'd see, like sunspots.
Yeah.
In white light, sunspots are quite dramatic. They're really dark, and when you get a lot of them clustered on the disk, they really can be quite dramatic, and watching them move over time, I think, is quite
That's right,
fascinating.
because you can see the sun rotate, the effects of the sun's rotation. You can see them slowly drift across the face of the sun.
Well, let's move up to the higher end, i.e. your area, more expensive end. We're looking here at something like this. This is a hydrogen alpha telescope, so this
Yeah.
is looking at one of those colours of light. And
That's right.
This returns those beautiful red images. I've seen those images of yours, Pete. Lovely red images of the sun. You can see a lot more. The sun takes on a completely different form in this, doesn't it?
That's right, you're looking at the sort of glowing hydrogen just above the visible surface
Yeah,
of the
it's
sun.
beautiful.
And that's actually what our footage is about.
One of the things, as you said, that this sort of telescope reveals is just how dynamic these objects are.
Oh, that's right. I mean, when you're imaging the sun, you can actually see changes in features after just a few seconds.
These incredible images are from telescopes in space, which stare unblinking at the sun's raging atmosphere. The reason the sun, our star, is constantly changing is because it's a writhing sea of hot, ionized gas known as a plasma, and it's powered by a nuclear reactor in its core. The churning of the plasma strengthens the sun's magnetic field, causing it to burst through the surface and out into space. Dark sunspots are formed where strong magnetic field traps gas at the surface and it cools down. At Greenwich, they have been looking at sunspots for over 100 years. Marek Kukula is an astronomer with the Royal Observatory. Although he normally looks at galaxies, he showed me the telescope that was once used to document the sun's every move.
So this is a photoheliograph, one of several that belong to the observatory and were sent all over the world. And as the name photoheliograph suggests, it was used for photographing the sun. And I actually have here a glass plate that was taken using one of these instruments. It may even have been this one here. And this is from 1917. Ooh. And you can see it's a beautiful plate showing a negative image of the sun.
I can see on here that it says that it's taken in the K line, which means calcium K filter was used, looking at the chromosphere of the sun.
So this isn't the whole of the light coming from the sun, just a tiny fraction of it?
Just a tiny, tiny fraction, and it allows you to see a particular layer of the sun. And what's really nice is that you see these two bright regions here, and that's formed by the locations of very strong magnetic field, or sunspots. And
so my field is galaxies, not the sun, so I'm kind of these look bright, but it's a negative image, so they're actually dark.
So they're actually dark, that's right.
Right, so they are sunspots.
These are the sunspots. And what's really lovely also is that they're near the centre of the sun. And since sunspots produce big eruptions into the solar system, it might be that these sunspots back in, when's this, 1917, produced an eruption that reached the Earth and triggered the northern lights. We'd have to check the dates.
The early work by Greenwich astronomers established that the sun has a cycle. They were able to see a pattern in the number of sunspots, where the number rises and falls roughly every 11 years. Called the solar cycle, it has a maximum and a minimum, where the sun moves from being active to quiet and back again.
There is an archive of these images that were taken day after day here in Greenwich and at other royal observatories around the British Empire. And I guess they go back into the 1870s. Are these still useful to you as a solar physicist today?
They are. We're really, really interested in the solar cycle, but we want to know how the sunspot number has changed over the last decades, hundreds of years, I mean ideally thousands of years even. But the archive that Greenwich has means that we can check back to the 1800s and look at the sizes of the cycles, right. See, are they always regular, how do they change? And at the moment, even though the sun's at solar maximum, it has been showing that it's a little bit quieter in this cycle than it has been in previous ones, and that's a big question in solar physics to try and understand why that's the case now.
So the work that was being done on instruments like this back in the 1800s, that still actually has some relevance to solar physics today?
Still, the archive is incredibly important.
Well, it's good to know that Greenwich is still contributing in some way to modern physics.
I'd like to have a go on this telescope, I have to say.
We'll bring you back on a sunny day.
Seeing sunspots and other features evolve and change quickly is one of the pleasures of solar observing. Looking at the sun is something even beginners to astronomy can enjoy. Christina and Caroline have bought their first telescopes, and they want to know how to look at the sun safely. Who better to ask than Pete and Paul?
Over there we have Keaton, he's holding up the sun. This is your moment, Keaton, it's arrived.
He's been there for hours.
In that position. And so what we would do then, if we wanted to find the sun, the first thing to do is to remove the viewfinder. So this one just slides off here.
Yeah, and that one
Why
too.
do you remove?
That's a good question. We remove it because otherwise the sun's light will come streaming down and it's enough to cause damage. So we want to be very safe. So before we go looking for the sun, the first thing we need to do is filter our telescopes, and I have some stuff here I grant you, looks like ordinary tin foil, but it's not.
So it's not the type in my kitchen drawer?
No, leave that in the kitchen draur, because if you use that, blindness will result. We don't want that. So here you go, have a look. This is the sheet we tend to use. It costs about 24.
It's about £20 for an A4 sheet.
Yeah.
In fact, there's a filter down there, if you can grab that one. That's what you have to do, is take that stuff and with a bit of DIY using some highly technical cardboard, sellotape and scissors, you can make your own filter. And if you're wondering how you make that, we've actually got instructions on the Sky at Night website. So that's bbc.co.uk/Sky at Night. There is a little bit of film on there showing how to make that filter.
So once you've made the filter, how long will the filter last? Is it, as long as it's intact, it lasts?
If you look after it, it'll last for a long
You
time.
may always see if it's damaged just by holding it up and if there's any holes.
That's a very good point, actually. Yeah, before you put the filter on, it's always a good idea to hold it up to the sun so that if any light's coming through and it's ripped, throw it away and just make another one.
Okay, brilliant. If I didn't have a lot of time, could I not sort of just quickly put the foil over the front of it and put an elastic band round it that way?
That's an excellent question, and it brings up the fact that you can't do that really. You need to make sure that the filter fits securely over the front of the telescope, and it certainly can't come off. If the wind were to blow it off or the elastic band were to unfurl and it pinged off, that would be disastrous.
Okay,
absolutely don't do
that.
that.
So it's not worth cheating?
No, definitely not.
Once you put this over the top, do you have to tape it down or fix it?
I do. I always put a bit of sellotape on just to make sure the thing stays on.
It doesn't need to be a solid, just a tack of tape, or just to keep it firmly there, I think is a good idea, actually.
You can't be too safe, and why take the risk? So sellotape, no elastic bands, make sure the thing stays in place and no danger of it coming off.
On the Sky at Night Flickr page, you can see amazing images taken by amateur astronomers. They show material lifting off the sun, called prominence eruptions, explosions called solar flares, and some of you have even managed to capture the biggest explosions the sun makes. It's staggering the detail that many of you can see using your telescopes.
Well, so far we've mostly been talking about the sun's surface, but it does of course have an atmosphere as well, and all sorts of things happen in that atmosphere.
And the atmosphere has a temperature of 1,000,000 degrees, which is too hot for the sun to contain it, and it streams out into the solar system, doing something similar to what happens when I blow up this balloon.
So what's coming out of the sun is a stream of particles called the solar wind. The sun is in the middle of Lucy's balloon here, and that solar wind spreads outwards. These particles push outwards through the solar system, and they form a shape pretty much like this.
That's right, so the solar wind is contained inside, and outside is the material between the stars. And sometimes the wind blows very strong and inflates this bubble.
Which we can demonstrate like so, very good.
And sometimes it blows more weakly, and the bubble deflates.
And just like there's air pushing down on this bubble to give it this shape, outside the solar system there are particles and the rest of the galaxy which shapes our solar system too. So this is the edge of the sun's influence on the rest of the galaxy.
And also, because the sun is moving through the galaxy, it's pushing against the material of the galaxy itself, and it creates a kind of teardrop shape that's compressed at the front and drawn out at the back, a little bit like this balloon.
And that's maintained by the fairly constant solar wind that the sun's pushing out all the time. But just sometimes we get a really spectacular event on the sun. The sun loses 1,000,000 tons of mass every second, and that mass streams outwards into space in the lumpy and gusty solar wind. Chris Davis studies that solar wind, represented here by his bubble gun. As material constantly flows outwards, because the sun and Chris are rotating, the result is a spiral pattern. Chris uses two spacecraft called Stereo to study a very special set of eruptions, coronal mass ejections, which are both spectacular and powerful.
Well, a coronal mass ejection, a typical coronal mass ejection, contains about the same energy as about 100 times the entire world's nuclear arsenal.
That sounds pretty scary.
It's an astonishing amount of energy. But a colleague of mine worked out before lunch once that it was also equivalent to the energy in a Mars bar if it were about 2,000 kilometres long.
Excellent. Well, I'll remember that. And so what's happening to these particles as they travel outwards through space? Are they interacting with the surroundings? Are they spreading out? How should we picture that?
Well, it's like a magnetic bubble bubble which has lots of electrified gas, plasma, as it travels out. As that bubble expands, that gas is expanding with it, so it's getting more and more tenuous, more thinner as it comes out into space. Now, the solar wind is very few particles. It's about maybe 5 to 20 particles per cubic centimetre. So in a volume about this big,
There's only got 5 particles.
There's 5 particles, so it's almost nothing. And it's a really peculiar thing that this wind that is almost not there actually can slow down mass ejection as it emerges into it. And that's because these particles are electrified, they have magnetic fields with them, and so they can interact. They actually behave like a fluid.
In July last year, one of the stereo spacecraft was temporarily blinded when a coronal mass ejection hit it head-on. The NASA satellite SDO was able to image the area of the Sun that eruption came from. If that had been in the direction of the Earth, it would have knocked out our mobile phone system, our satellites, and even our television. Not good news, but even the ordinary solar wind can have dramatic effects.
Luckily for us, we have a natural shield against these damaging particles coming from the Sun, in the solar wind and the eruptions, and it's our magnetic field. So similar in shape to the one created around this bar magnet, molten iron within the Earth creates a vast magnetic bubble extending thousands of miles above our heads. And normally the particles from the Sun flow around us. But sometimes our magnetic bubble gets energised and currents start flowing down onto the top of our atmosphere and lighting up the gases as they energise it. Oxygen shining green and nitrogen shining blue and red. And that's when we have the displays of the northern and southern lights, or the aurora.
The aurora borealis, or northern lights, are truly wonderful to look at. But the story of their origin has a violent and cataclysmic beginning. A huge coronal mass ejection erupts on the Sun, launching billions of tons of plasma out into the solar system in a magnetic bubble, and we are in its way. It slams into the Earth's magnetic field, and if conditions are right, our magnetic shield starts to open up and distort. This causes charged particles from far above our atmosphere to race down the Earth's magnetic field lines. They reach the top of the Earth's atmosphere, energizing the oxygen and nitrogen particles and causing them to glow. It's this which creates the beautiful and mesmerizing aurora borealis.
Last year, Lucy and I went to Svalbard in the Arctic Circle to see the transit of Venus. But we took some time out to visit the radar station, IceCat, which is looking way up into the top of the atmosphere, where the aurora dance day and night. Lucy explained to me how the aurora form.
The Earth is sitting in the Sun's atmosphere in this wind, and it's a bit like a pebble in a stream. And a lot of the time, the wind flows over the Earth's magnetic field. But sometimes when the conditions are right, the magnetic field of the Sun can connect to the magnetic field of the Earth. And so I visualise lines of magnetic field that break and join. And it happens when the Earth's magnetic field is pointing in one direction and the magnetic field coming in the solar wind is pointed in the opposite direction. And then the field lines can break and rejoin. The technical word is magnetic reconnection, which does what it says on the tin. It connects the magnetic field from the Sun to the magnetic field of the Earth and then channels those charged particles coming in the solar wind onto the Earth's magnetic field lines that ultimately can then spiral down and come to the skies above our heads here.
In Svalbard in summer, the sun never sets, but IceCat can still keep working. Aurora watchman Ian McCrea is at work right now, looking at the very top of our atmosphere, a region called the ionosphere.
Actually, we have had quite an active day.
smooth ring. But when it gets to a certain point, the water, or the solar wind, slows down just enough and suddenly gets much more bubbly. You can see ripples and bubbles
I can see bubbles around here. So there's a kind of circle, and then beyond that, where the water or the solar wind has slowed down, it's very bubbly.
Yeah, and that's the reason that the Voyager spacecraft are in now. And they've seen these bubbles. They were a complete surprise. We thought it was going to be nice and smooth, and there'd just be a gentle transition to interstellar space eventually, which they're heading towards. And these bubbles are absolutely massive. They're magnetic bubbles in the solar wind.
We don't know when the plucky, pioneering Voyagers will reach deep space, but their batteries will die in 15 years' time. Our journey to the edges of our solar system has also drawn to a close. The sun has set over Greenwich, and even though it's below zero, the Flamsteed Society have bravely joined us with their telescopes to keep us company. The green laser, which marks the meridian line, or 0 degrees longitude, is shining brightly.
Well, here we are, Pete. We're at Greenwich, and the lovely Flamsteed Society brought all their telescopes, but there's nothing to see because of the clouds.
What a typical sky at night.
So never mind. We do have some things in February. An asteroid, see if I can remember the name, 2012 DA14.
You've been practising that, haven't you?
It's such a delightful name, isn't it?
It trips off the tongue,
It
yes.
does. Now, this is interesting because it's going to pass very close by to the Earth, isn't it?
Yeah, it'll pass us by about 35,000 kilometres. And when you bear in mind that geostationary satellites, those are the satellites which sit above the same point of the Earth, and they deliver things like satellite television, for example, they're about 36,000 kilometres out. It's actually going to come within that.
So it's going to pass up in between them. Actually, we should say there's no danger of a collision or anything like that, and it doesn't rise up where we are till about 8 o'clock in the evening.
No, that's right.
But the best time to look at it is really around 9:30, 10 o'clock.
Yeah, I mean, this isn't a very large object. It's about 45 metres across, and that means that it will actually become bright enough to be seen with binoculars when it's at the closest point. But we're picking the point between 9:30 and 10 o'clock because that's the time when it crosses the tail of the Great Bear.
Right.
So the plough, or the saucepan as I call it. So if you locate the star in the upper left corner of the pan, and then the next one out along the handle, it's going to cross that line between 9:30 and 10 o'clock. Get with a low power eyepiece, should be able to pick it up. So go out and give it a try.
On special nights, the Royal Observatory welcomes the public to the dome of the 28-inch telescope, and Lucy and I joined that public tour. The 28-inch is over 100 years old and was the workhorse of the observatory, used every clear night to study the stars. Little's changed from those early days when astronomers had to lie on their backs to look through the eyepiece. The telescope was moved briefly to the darker skies of Sussex, but then, in 1971, it came home. Patrick and the Sky at Night were there to celebrate the return to Greenwich of this astronomical giant.
This is an historic moment at Greenwich Observatory. The great 28-inch telescope is coming home where it belongs, at the old Royal Observatory in Greenwich Park. Inside the observatory, everyone's waiting for the first of the really big lifts, the North Pier. And the mounting's going to exactly the same position as they had in 1857. And only after both piers have been firmly cemented down will the telescope, in its axis, be balanced and secured between them. It's not the end of the story by any means, because remember, it's going to be used, and therefore it's got to be very carefully adjusted, and this is going to take some time. But in the foreseeable future, it will be fully operative again, and it's good to know that the old Royal Observatory, Greenwich, has again got a great telescope.
The 28-inch is still used by astronomers today, no longer for research, but to enjoy the wonders of the night sky.
Tonight, as you know, it's a little bit cloudy out there, so unfortunately we can't peer through the clouds. It's the one thing that we haven't mastered as astronomers just yet. We haven't got control over the weather systems. But it does give us a chance to show off our biggest telescope here at the observatory, and also the 7th biggest telescope in the world of its type. It's a very special type of telescope called a refracting telescope, and there are 2 lenses at the very top of that instrument, and both of them together weigh 200 pounds.
This telescope is fabulous. It's wonderful to see it back after 120 years. It's so elegant in the way it moves around, so easy to move. I just wish it were clear so we could see something.
Here's some footage of the moon taken through the 28-inch telescope showing the Alpine Valley and the craters Archimedes, Aristillus and Cassini. I think Patrick would have enjoyed these.
We've had a marvellous time here at Greenwich, and a big thank you to the Flamsteed Society for turning out on such a cold, wintry night.
Next month we'll be up in Northumberland at the Kildare Observatory, hoping for better weather and to catch a glimpse of that asteroid as it whizzes past.
And we'll be bringing you the results of the Moore Winter Marathon, so well done to everyone who's taken part.
So until next month, from Greenwich, good night.
Stay with us tonight. The boys are in danger of getting their fingers burnt in Way to Go, coming up in 10 minutes. After a spot of music next.
This is the first map of the Milky Way made by William Herschel back in 1785 in a paper he called On the Construction of the Heavens. And it's a wonderful thing, but it's not that accurate. It shows the sun at the centre, which is wrong. There are no spiral arms. But he did get one important thing right. He shows the Milky Way as a disk seen almost side on.
Since then, our knowledge of the Milky Way has greatly improved. But these images are actually artists' impressions. We think that the Milky Way looks like this, but we don't know for certain. In fact, we know surprisingly little about our home galaxy.
But a revolution in our understanding of the Milky Way is underway. And the more we learn about our galaxy, the more surprising and interesting it becomes.
So tonight, we bring you the bang up-to-date guide to our galaxy with the most exciting and unusual discoveries.
Welcome to the Sky at Night.
Like all good guides, ours will include the best maps available, the most interesting destinations, and of course, a bit of history.
We're down. We'll be joined by guest presenter Neil deGrasse Tyson for a tour of his top 5 strange and spectacular stars.
This white dwarf is effectively flaying the outer layers of this giant, consuming it, body and soul.
Pete will show us how to find some of the highlights of our galaxy in the night sky. But first, we're going to start with the most essential part of any guide, the map.
We're here at the Institute of Astronomy in Cambridge, where the researchers have been making the most detailed and the most accurate map of the Milky Way ever. To do that, they're using one of the most impressive space telescopes ever constructed. If it were here on Earth, it would be capable of measuring the thickness of a coin on the moon.
In December 2013, the European Space Agency launched the Gaia Space Telescope. Its mission, to map the stars of the Milky Way in unprecedented detail. Gaia is actually 2 telescopes, each observing 100,000 stars per hour, and capturing the data with a 1 billion pixel camera, giving Gaia a resolution that is 10 times greater than most ground-based telescopes. Over its 5-year mission, Gaia will observe each part of the sky 70 times in order to measure the exact positions of the stars, their distances, and their motions. This room is where data from Gaia comes pouring in and gets processed. It's effectively the nerve center for understanding our galaxy. You get some idea of the scale of the data processing operation in here. This supercomputer is made up of 1,296 processing cores. But this is just the tip of the iceberg. There are 5 more centers like this dotted around Europe, all handling Gaia's data. To convert raw satellite data from Gaia into an actual map of the Milky Way with precise positions, distances and brightnesses is no mean feat. In fact, for the first batch alone, they've had to analyse around 120 billion images. And to achieve the incredible precision required by the Gaia mission, the data processing teams have to try to correct for every possible source of error. They even have to account for the gravitational influence of the other planets in the solar system on the light from the stars. It's a tremendous task, so much so that it took a year to process the first 14 months' worth of data. But it's been worth all the effort, because the result is nothing less than the first truly accurate map of our home galaxy. And Chris went to meet lead scientist Jerry Gilmore to see the map for himself.
So, Chris, welcome to our new map of our Milky Way.
It's beautiful.
You see immediately the sort of big picture structure. First thing to notice is that this is a map of the entire sky.
But this stripe across the middle, this bright stripe, that's the galaxy.
That's the Milky Way galaxy, that's right, yes.
But there is more to the Milky Way than just the main disk. There are also millions of stars both above and below the disk. Everything white that you can see in this image is starlight.
What we need to do is zoom in. So this is the top layer map, and now we're zooming in. So this is the inner parts of the Milky Way here, these big dust clouds and dust lanes, the dust lane. These are dust lanes, and you start to see that all the white light is now breaking up into stars, into individual
stars. So as you get further in, as we zoom in, we see more and more stars individually.
Absolutely. Look at how they suddenly appear as you go that little bit deeper into space, and bang, what you thought was just white light is actually starlight.
And how many stars are there in the galaxy?
There's maybe 100 billion, 200 billion, 300 billion. So the number's probably near the high end of that range. What we know is that there's maybe twice as many as we previously thought.
There are twice as many stars in the galaxy as we thought?
That's right. Yeah, it's just in the bit of the Milky Way that Gaia has measured. There are twice as many stars in it.
How has Gaia doubled the number? That seems surprising to me. I see that you didn't know the position before, but where have they been hiding?
It's just because of the image quality of Gaia. The fact that Gaia has such high spatial resolution.
Because it can see sharply.
Exactly, it sees sharply. And so Gaia can tell the difference between 2 or 3 stars that are very close together, but nevertheless are separate stars, whereas previously, from our images from the ground, blurry sort of things, this stuff here would have all been merged into what we thought was one star.
And so we've been looking at the map as it appears on the sky. But one of the exciting things about Gaia is that we have 3-dimensional information as well. We can go beyond this sort of 2-dimensional picture.
Exactly, and that's the unique feature of Gaia. Gaia measures distances as well as all these other things. And once we get into measuring distances, then we can measure the 3-dimensional structure of our Milky Way. So far, we've only just had a taster of that. So Gaia's just released 2 million accurate distances. And so here is the beginnings of a picture in 3 dimensions. This is our sun. And we're about to go and see the Hyades and the Pleiades cluster.
Nice part of the autumn sky. Yeah, oh look, there's Betelgeuse and the Hyades there with Aldebaran in front of them, the Pleiades in the corner. There goes Aldebaran, it's closer to us.
And so here we are, for the first time ever, seeing a star cluster in 3 dimensions. So we can tell the difference between the front side and the back side of the Hyades. So we know exactly in 3D where all these stars are.
And this helps understand the cluster. We know more about it than we did before we had this map.
And so we have already discovered not only how deep the Hyades cluster itself is, but actually it's about twice as big.
It's amazing. What other features should we look for in this 3D map?
So this dramatic Hyades example, one very nearby cluster, is just a taster for what's going on. We've got good distances now for just 2 million stars. We're going to have 1 billion at least. That will give us a 3-dimensional map of half of our Milky Way. But even more interestingly, because Gaia's continuing to observe over time, it's telling us how everything's moving. And that combination of where things are and how they're moving allows us to determine how the galaxy works as a machine, how the Milky Way actually functions, what is the spiral arm, where is the dark matter, and how it's evolving.
Well, it's going to be very exciting.
Going to be fantastic.
So now we have a map of over 1 billion stars in our galactic guide. But the question is, where do we go and visit? What are the most interesting and exciting stars within our galaxy? We invited astrophysicist Neil deGrasse Tyson, who has written about this very subject in his book, Welcome to the Universe, to give us a guide to the weird and wonderful stars of the Milky Way.
The sun It's 1 million times bigger than the Earth. It's widely regarded as a yellow orb in the sky, but it's actually white. You know, our sun is not the hottest or the coolest or the biggest or the smallest. There's nothing to distinguish it among the hundreds of billions of other stars in the galaxy. In fact, if you were an intergalactic alien and you came upon the Milky Way, there'd be nothing about our star system that would attract your attention. But there's plenty of other stars in our galaxy worth a look. And I've made a personal list of the top 5. Coming in at number 5 of our exotic star countdown of the Milky Way is SAO 206462. Previously thought to just be an ordinary star, when you go in and look close and you blot away the light of this relatively new star that was just formed, you get to see this remarkable spiral structure. We're pretty confident that this is a disk of debris in the act of forming brand new planets around this relatively newly born star. Each of these spiral arms will likely coalesce and in the not so distant future become single planets, one for each arm, in mutual orbit around the host star. We've seen disks of material before around newborn stars, hinting that planets are soon to form. But this is the first time we've ever seen spiral structure. This star is just at the beginning of its life, and who knows what other strange phenomena it will treat us to as it evolves. But strange behavior isn't the preserve of the young. Coming in at number 4 among the top 5 weirdest stars in the Milky Way galaxy is Omicron Ceti. Ceti referencing the constellation Cetus, the whale. Here it is. It happens to be a red giant star. Plenty of these in the galaxy. Not even distinguished for how it looks in visible light. But if you instead observe this star using ultraviolet, this is what you find. The star is up here, and there's this long 13 light year plume left behind. And right up front, we have a bow shock, which is evidence that this thing is plowing through the galaxy between the stars at incredible speeds. In fact, we can measure it at 300,000 miles an hour. We happen to know that red giants only have a tenuous connection to their outer gaseous shells. So going that fast, it's going to lose some of that outer shell, leaving it behind as it punches its way through the gas of the interstellar medium. We've never seen anything like this. But the most spectacular sights to be seen don't just involve one star. Coming in at number 3 is MY Camelopardalis. It's not one star, it's 2. 2 supermassive, hot, blue stars in orbit around one another. That alone is not odd. More than half the stars you see in the night sky, if you pull a telescope out on them, what you'll notice is that it's a double or multiple star system. So we're cool with that. What's different here is that these 2 stars are in contact with one another. We are fairly certain that given enough time, these 2 stars will completely coalesce, joining their fuel supplies into one coherent star. What we don't know is, will that star be stable and just join the ranks of other high-mass stars that are out there, or will it be unstable and blow itself apart? We don't know. Just keep watching this space. This isn't the only strange binary system to be seen. We're down to number 2. That distinction goes to Gaia 14 AAE. Once again, it's not a single star, it's a binary star system. In this case, one of them is a white dwarf, the end stage of a medium-mass star, such as the Sun, and a companion star, which happens to be going through its giant phase. This white dwarf is effectively flaying the outer layers of this giant, consuming it, body and soul. It's basically a stellar cannibal. If the growing mass of the white dwarf crosses a certain threshold, the white dwarf will go unstable and explode, become a supernova. But this isn't even the weirdest thing that can happen when stars collide. And now, the #1 weirdest star in the Milky Way galaxy. It goes by the name of V Hydra. This star, a red giant star, would not otherwise call attention to itself were it not for every 8.5 years, blobs of nearly 10,000 degree plasma come spewing out at 500,000 miles an hour. Then it stops. 8.5 years later, it repeats. Who ordered that? Our best hypothesis is that this red giant star has a companion, another star in orbit around it that has a highly elliptical orbit, a highly elongated orbit. Spends a lot of time out far away, but when it comes in close, it comes in real close and punches through the physical body of the red giant itself, pops out the other side, and we think that interaction of a hot star and the red giant is what's responsible for spewing forth these blobs of plasma right on schedule every 8.5 years. So we've never seen this phenomenon before. We think we have the right explanation for it, but it remains a unique object in all the star catalogs that we've accumulated. And for that reason, it is the weirdest star in the Milky Way.
And if you want to see some of Neil's top 5 stars for yourself, Peter's here to show you how to find them.
When you look up at the night sky, all of the stars you can see individually belong to our own Milky Way galaxy. Now, in the winter time, the dense part of the Milky Way, which is towards the core, isn't visible. But when we look up at the sky in the winter time, we're looking outward in the opposite direction. But this is also a great time to look for some of the 5 must-see stars in the sky. Now, I'm going to start with Omicron Ceti, which is in the constellation of Cetus, the whale or sea monster. This is the comet-like star, which when viewed in ultraviolet is seen leaving a tail behind it as it races through the galaxy. Now, this is a variable star, and at its brightest, it's an easy thing to see with the naked eye. But at its dimmest, as it is now, you need a telescope or a pair of binoculars to pick it out. Now, I'm going to use my camera and see if I can take a photograph of the star. To find it, first identify the Great Square of Pegasus, and then below and to the left, find the faint V-shaped string of stars of Pisces. The string comes to a sharp point at the star Alresha, and this acts like an arrow pointing directly to Omicron Ceti, also called Myra. I'm actually finding it quite tricky to locate the field where Myra is at the moment. And the reason for that is that there is a full moon coming up, and that's making the sky really bright and drowning out all the faint stars. But I think I'm more or less in the right area now. And I think I've got it. There are 2 stars very close to one another. One of them is red, and that is Omicron Ceti, or Myra as it's known. And it's red because it's a red giant star. Now, I can't see the tail because that's visible in UV light, and UV light is blocked by the atmosphere, so that's best left to the space telescopes. But I've definitely got it, so I'm happy. And in the faint constellation of Camelopardalis, which lies to the north of Auriga and Perseus, is the merging binary star MY Camelopardalis. Now, this is so far north in the sky that from the United Kingdom it never sets, but you will need a telescope to see it. The best way to find it is to extend a line from the famous eclipsing binary star Algol through Murphak, the 2 brighter stars in the constellation of Perseus. Extend the line they make north for the same distance again, and you'll be in the right area. And if you're willing to stay up until the early hours, then you stand a chance of seeing the #1 strangest star in the galaxy, V Hydrae, the star system emitting the plasma balls. It lies in the belly of Hydra the water snake. Halfway along the snake, find New Hydrae, and 5 degrees below that, at the bottom of a Y-shaped pattern of stars, is V Hydrae. A telescope is the best way to see it. But sadly, the last two of Neil's favourite stars are too tricky to see. SAO 206462, the star with the spiral arms, is too far south to be seen from the UK. And Gaia 14AAE, the cannibal binary system, is extremely faint, so would be very hard to spot without a large telescope. This time of year is also great for seeing another of the stellar highlights featured earlier, the Hyades star cluster, which Gaia has mapped in 3D and which can even be seen with the naked eye. Now, the best way to see them is to use a pair of binoculars or a telescope, and if you use such an instrument, you'll see them in far greater detail. Now, I'm going to take a photograph to see what I can get. The easiest way to find the Hyades is to extend the line made by Orion's belt up to the northwest, or up and right as seen from the UK, until you arrive at the bright orange star Aldebaran, which is part of the V-shaped face of Taurus the Bull. So the face of Taurus the Bull is the Hyades, and the Hyades are about 625 million years old, so they're getting to the end of their life. So there are lots of red giants and white dwarfs in this cluster.
Our understanding of the Milky Way is improving all the time. Not only do we now have Gaia's billion-star map, but recently ground-based telescopes have created the most comprehensive map ever made of the distribution of dust in the galaxy. It shows the spiral arms, star-forming regions, and streams of dust. But beyond the stars and dust, there are other parts of the galaxy that we still know extremely little about. The final part of our guide to the galaxy takes us to one of the Milky Way's most mysterious and interesting regions, its outer reaches. It's long been thought that the visible disk of the galaxy is embedded in a huge corona, a vast cloud of hot, ionized gas, and if it's there, it might help us solve a problem. Because when you add up all the dust, all the gas, and all the stars in the disk, all the normal matter, you find there's only about half as much as there should be. And it may be that that missing mass is hiding in the corona. But we know very little about this strange enigmatic region, but scientists here have made a new discovery. Maggie went to meet Dennis Urkel to find out what this discovery can tell us about the nature of the corona and the missing matter in our galaxy.
So Dennis, thank you for coming up to speak to us. And this is a glorious picture. What are we seeing here?
This is a picture that I took in Chile. So this is the night sky as seen from Chile. So this is the Milky Way right here. This is the disk of the Milky Way. And these are the objects we're interested in. This is the small and large Magellanic Cloud. These are two dwarf galaxies that very recently they had their closest approach to the Milky Way.
These can only be seen from the southern hemisphere?
These can only be seen from relatively far south.
So what have you discovered so far?
So let's just zoom in a little bit. So this is another picture of the large Magellanic Cloud and the small Magellanic Cloud. This was the optical image, but we can also show what happens when we overlay data from a radio telescope. So this shows hydrogen around the large and the small Magellanic Cloud. So what we believe happened was, about a few 100 million years ago, the small Magellanic Cloud passed near the large Magellanic Cloud. And as it passed nearby, the gravitational force from the large Magellanic Cloud shredded part of the small Magellanic Cloud, ripping off this gas bridge.
Oh, wow.
And so now we can overlay this blue line, which just shows us the densest part of the gas. So we've known about this gas bridge for a long time, but what we found recently was a stellar bridge. And so this shows the data from the Gaia satellite. So here, the background image is the one I showed you before, and in white, this milky cloud shows the stars from Gaia smoothed over to make an artist's impression of the data.
Okay, so Gaia has discovered these stars, and it looks like, yeah, there's a stellar bridge, a bridge of stars.
That's right. So this is the stellar bridge coming down here. So just like the gas was ripped off from the small Magellanic Cloud, we think at the same time stars are ripped off.
So the gas and the star bridge were created at the same time and place. But there's a mystery. Because today, when the images are overlaid, you can see that the two bridges are no longer aligned. And Dennis believes The explanation for this discrepancy is the corona.
So the Large and Small Magellanic Cloud are both moving down roughly in this direction. So we think as they move through the corona, what happens is the gas gets pushed back by the corona from the Milky Way. The stars also feel that pressure from the corona, but since they're small and dense, they basically punch through the corona, so they don't get pushed back at all.
So this result is really good evidence that the corona actually exists.
That's right. There was some evidence before, but we think this adds even stronger evidence, so we're very convinced that the corona is there.
How far does it extend from our galaxy?
We think it extends out to at least 600,000 light years from the center of our galaxy.
Wow. But that's sort of well on its way to Andromeda, isn't it?
That's right. That's about a third of the way to Andromeda, so it's really far out. Wow. It goes at least that far, we think.
So with this massive corona around our galaxy, can that help account for the missing visible matter in our galaxy?
Yes, we think that this corona can account for a significant fraction of the missing normal matter around our galaxy.
Wow. That's quite a result, isn't it?
Yeah, it's pretty exciting.
There's another layer of significance to this finding, because there's evidence of a similar corona of hot gas around our neighbouring galaxy, Andromeda. Andromeda is about 2.5 million light years away, but it's on a collision course with the Milky Way. We've measured that Andromeda has a corona, and it extends halfway to our galaxy. And now we're getting this strong evidence that we've got a corona that extends a long way. Is there a possibility they could be touching?
That's right. It is very possible. From our models, we think it's very likely that the very outer extents of our galaxy and Andromeda are touching right now.
So I've often heard it quoted that in 4 or 5 billion years' time, the Milky Way and Andromeda will collide. But it sounds as if the collision's already begun.
In a way it has, yes, but these are just the very outer tenuous edges of the coronas of the Milky Way and Andromeda. But yes, the collision is starting to start now.
Well, I think that's pretty exciting. Thank you so much for coming in and talking to us.
Thanks, it's been a pleasure. Thank you.
Thank you.
The collision of the Milky Way and Andromeda will eventually create a new giant galaxy. It's extraordinary to think that the first contact between the two galaxies may have already begun, but it'll be another 4 billion years or so before the merger is complete. It turns out that this intergalactic collision will not be a new experience for the Milky Way, because Gaia has revealed that our galaxy is the product of many previous smaller galactic mergers. The main disk of the galaxy is surrounded by a halo of stars and clusters which live both above and below the disk like this. But what's new is that thanks to Gaia we can work out how this whole system is moving. Now the disk is rotating, we've known that for a long while, so it's spinning in this sort of direction. But what Gaia has found is that some of these clusters are moving through the disk and they're doing so in the opposite direction to the rotation of the disk itself. And so what that means is that these clusters are the remnants of galaxies which our Milky Way has accreted. Our galaxy is growing through galactic cannibalism. And this process is still going on. The Magellanic Clouds Dennis was talking to Maggie about earlier will almost certainly be eaten in the next few 100 million years.
That's it for now from our Guide to the Galaxy. But don't forget, our understanding of the Milky Way is undergoing a revolution. So tune in a year or so's time when we get the next batch of data from Gaia.
Next month, we have a special programme. We'll be taking over some of the telescopes under the clear skies of La Palma in the Canary Islands.
And we want you to tell us what we should point the telescopes at. Find out more on our website, and then email or tweet your suggestions to the usual addresses on the screen now.
And don't forget, you can already check out our star guide on the website.